Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Sophia Han with us today. Hey, Sophia.
Hi, Frank. Nice talking to you.
It's great talking to you. And where am I talking to you to? What is your geolocation?
Yeah, I am right now in Seattle. I am a postdoc at Institute for Nuclear Theory, University of Washington, with a joint appointment at UC Berkeley. But physically, I am now in Seattle.
Very cool. Very cool. So is it summer yet in Seattle?
It's not hot yet. I mean, it's cloudy and the temperature is relatively low. But I saw the weather forecast next week will be warmer.
Ah, very good. Yeah. I've been up in Seattle in the summer, and at times it's actually quite pleasant when the clouds.
Right, summer is actually the best season in Seattle.
Yeah.
Not many raining days.
Yeah. No, it was really pleasant. I was actually visiting the INT at the time when I was there in the summer. It's very nice. Here on this May 26th, it's a little cloudy in Phoenix, which is fairly unusual for this late in the spring or early in the summer. We haven't quite hit the power switch still, but we will. So are they allowing people to go into the INT, or is it still mainly virtual? Or
not yet? Yeah, I heard a discussion about returning back on campus maybe in July.
Oh, okay.
Yeah, but there are policies being discussed about different phases to go. And possibly for us postdocs, we are among the last group of people to be allowed to go back in offices.
Right.
Yeah.
So we are here at Arizona State University. We are planning a full in person, and we start in August, early August.
I see.
Be fully back and operational, hopefully relatively risk-free when we start in August. So.
Right. Yeah. Sounds exciting. Haven't seen a single physicist since last March, I think.
In person, anyway.
In person. Yeah.
I was gonna say, if you haven't seen any between in person or virtual, then yeah, that's like a withdrawal of some sort. Oh, goodness gracious. Well, you get a chance to talk a little bit about some physics today.
Yeah.
So speaking of, Sophia, what is it you like to do for research?
So my research mostly focus on studying phases and properties of cold dense matter on the QCD phase diagram. And these are very special things because we can only find them in the dense cores of neutron stars, only in astrophysical conditions. In particular, I am working now on constraining the high density equation of state, which is the relation between pressure and energy density for such form of matter in the neutron star dense cores. Basically, we can do such constraining efforts from many different perspectives, but most importantly, there are various neutron star observables made possible by multi-messenger astronomy, but also we would like to still take advantage of developments in, for example, low density nuclear theory and laboratory experiments. They are complementary, but still quite useful.
Indeed. Cool. Very nice. And that is going to bring us to this very lovely APJ article on the minimum radius of very massive neutron stars. And Sophia, take us away.
Thank you. Yeah, so this is a paper we published last year, about one year ago, right? The motivation for this work is actually the first data from the NICER mission, the Neutron Star Interior Composition Explorer, back in December 2019. There was the first ever simultaneous measurement of the mass and radius for one particular pulsar. And that measurement is important in terms of constraining the equational state relevant for canonical mass neutron stars, typically about 1.4 solar mass neutron star. And we actually collect up-to-date measurements in table 1, I think.
You want to go down to table 1?
Yeah.
Go down to table 1 and take a peek at.
Yeah, table 1 and table 2. Yeah.
Okay.
Is what we described in the introduction, but mostly the motivation is because we, for now, only constraints on the canonical mass or radius of neutron stars, kind of the major part of our information is from this class of neutron stars. But since NASA promised to also look at targets with very high mass, about 2 solar masses,
Right.
then we think it's a good time to look into more detail about what, for example, a specific measurement of radius of a 2.0 solar mass neutron star can tell us
Very nice.
about the equational state.
Yes, very cool.
Yeah. And that is the motivation. And on the theory side, we do not have much control on the high density equational state, primarily because the experiments done in the lab only going to constrain nuclear matter properties at low densities.
Yeah.
And this is important because neutron stars, even a very light neutron star like 1.1 solar mass, usually they have already achieved their central densities as high as twice the saturation density of nuclear matter, which is out of the region that nuclear theory or nuclear experiments can probe. Therefore, what we do, or theories usually do, is to just speculate what the form of pressure versus energy density will look like at densities higher than that specific value. And for example, we do not know the relationship between epsilon versus P beyond certain density. And that will give different predictions for the categories of the mass versus radius.
Yep, I'm with you.
And the idea is to survey all possible outcomes if we just relax our constraint on the high density behavior of the pressure versus energy density. A particular observation of high mass neutron stars, is it possible to distinguish those different forms of the US at a high density? Right. And that is basically what we draw, how we draw this schematic diagram in figure 1.
Okay.
Yes.
There we go. Strange quark stars, hadronic stars, and third family stars.
Right. And this is just very briefly, it's not based on any realistic calculations, but in general, we have very different features based on what the equational state look like at high densities, which we also show in figure 2. And schematically, there is one-to-one correspondence between the different panels here.
Okay, yep.
Yeah.
Yep.
So the most ordinary case we are familiar with, like standard nuclear models, predict are represented by the middle panels. Yeah. So usually we have relatively small change in the radius for neutron stars from 1 solar mass up into 2 solar mass, which is close to maybe the maximum mass of the neutron stars.
Got it.
Yeah. So basically, the 2 dotted lines indicate where the radius for 1.4 and for 2.0 solar mass neutron star would be.
Okay.
And although there is a spread in the difference, typically for standard models, that difference is quite small, within say 1 or 1.5 kilometers. Yeah, for most microscopic nuclear matter equation state. It's a bit constraining if you have this three option where R2.0 is slightly larger than R1.4, because usually we would need a very rapid stiffening, which means the pressure has to rise relatively quickly from 1.4 to 2.0 to explain such a feature.
Right.
Yeah, although the equational state itself is still kind of smooth and continuous. Yeah, you can have a look at this panel B in figure 2. And the curve itself is smooth in some way, and most simply can be achieved in standard models. And I have been alerted to this by a previous study on special crossover equational state where you can have quark ionic matter, which means they have a mixture of quarks and hadrons in an unconventional way. And the equational state will be still continuous, but there is actually exotic degrees of freedom in the composition of the star. But still, you cannot tell it from a standard model of non-exotic degrees of freedom. And that's included in this case 3 of panel B, actually. Still panel B, not panel C. I'm still talking about, yeah.
I'm with you.
So this case 3, where R2.0 is slightly larger than R1.4, has a special candidate, that there is a some form of smooth transition in addition to the standard hadronic case. It is not a candidate to be distinguishable because you cannot tell the difference. But that is a kind of a new update from the theoretical side, because the quark ionic models are developed very, it's a very new idea, not until the recent years. The third panel is another possibility, which is, on the other hand, maximally distinguishable. So panel C, where I show this mass radius for so-called subfamily stars. Yeah, and you may realize the corresponding EOS, panel C in figure 2, is also very distinctive, right? Yeah, so basically, this is the scenario where we still assume low density matter is nucleonic, following the descriptions by low density nuclear theory, but at some critical value of density, as we go deeper and deeper in the neutron star, at some high critical density, a phase transition into some form of other higher density matter occurs. And if that transition is of first order, it introduces a discontinuity in this energy density.
Yes.
And you can see this delta epsilon, which is characterized the strength of that transition.
Good.
Yeah, so as we keep going into the center of a neutron star, now we are in some new form of matter, which we do not have a good idea about what the equational state looks like. And the first order approximation, or leading to in order, we can approximate that by a simple straight line, basically. That is what is depicted, yeah, right there.
Yep.
So this combination of two separate form of matter is actually going to give rise to very interesting features on the neutron star mass versus radius. And the most important or most interesting one is shown on panel C, figure 1, that you can see the dashed lines where we have hit that critical density of phase transition, the radius undergoes a very, very drastic decrease, right?
Yes.
And now, if we look at the relation between R 2.0 and R 1.4, they can be separated by something like 2 kilometers or even 3 kilometers.
Okay.
So this is definitely an observable.
Yes.
If we have future data to, I mean, many data to be collected and show some evidence of such a discrepancy.
Mm-hmm.
Yeah.
Cool.
Right. And this is basically what we start with because of many different scenarios. The most extreme case we also included, but very non-standard, is panel A for strange quark-stars. So this is the extreme case where we have these self-bound neutron stars, mostly made of quark matter, and they have a sharp surface with finite density. There is no nuclear matter actually on the surface of neutron star. So one would say, oh, this is in contradiction with what we observe. For example, we do see surface emissions from neutron stars. Mm-hmm. However, these type of stars, they can stand by their own, right? They can be a separate family. They are not ruled out simply because we cannot see them. It is theoretically still a possibility, and that's the reason basically why we keep the special case of strange quark stars or self-bound stars in this study. Yeah, and most importantly, they do provide a very important limit on the minimum radius. True. As we actually, elaborated later in the paper.
Nice. Yeah. Very good.
So so later we proceed to describe how these different equational states would look like on the relation between R 2.0 versus the maximum mass of neutron stars. So maybe we can briefly look at equation 1 and equation 2 on page 4. Yes. So equation 1 is just a simple parameterization of the self-bound stars, and it's just using a linear equational state with our specified value of the sound speed, which we call the CQM squared, stands for speed of sound in the quark matter. And this B is this back constant. So basically it is background pressure, like in the MIT back model. And specifically you have a surface with zero pressure, but the energy density is already some finite value, usually higher than the nuclear matter saturation density.
Okay.
And this is just a simplest equational state you can have. However, it provides an ultimate constraint, ultimate limit, if you specify, for example, the sound velocity to be 1, which is causality.
Yes.
Right. So then the only remaining parameter is this B, this back constant. And this is going to be determined by the maximum mass of neutron stars. So there is a one-to-one mapping between a value of M max, one assumed, and the equational state for this particular strange quark matter self-bound neutron stars. It's very clear that if we have maximally stiff matter plus conservative estimate on the maximum mass of neutron stars, then this will determine the smallest possible neutron stars for all masses.
Yes.
Yeah.
With you. Uh-huh. Mm-hmm.
And if we relax our constraints a little bit, saying, oh, there can be nuclear matter on top of this kind of self-bound strange stars, we are saying the transition density is some finite value below which we still have nuclear matter, and above which we have this simple form of quark matter. That is equation 2, basically. Yes, exactly. So we call this critical pressure for phase transition P trans. And below the transition density or transition pressure, we have some normal form of nuclear matter, and one can select their favorite one. Is epsilon nm as a function of pressure. And then by specifying 3 other parameters where this transition happens, that is P trans or epsilon trans. Second, how strong that phase transition is. Remember in the schematic plot, I showed this jump delta epsilon. That is the second parameter.
Yep.
And the third parameter is about what the stiffness in high density phase after after the phase transition already takes place. That's the third parameter. This is CQM. Yeah. So basically, by specifying these 3 parameters of a phase transition and also a hadronic baseline equational state at low densities, we can do a survey of all probabilities of neutron stars this type of equational state would give rise to. Yeah, and the limiting case is, of course, when P trans is at 0. We are back right to the very simple self-bound star case. Yeah. So we start from this simple parameterization, and realistic high density equation state may have a variation in their speed of sound. It's not necessarily a constant, but yeah, we have done work before. The nearly constant speed of sound is kind of an average estimate for all different observables, such as mass and radius, because you can always replace the value of CQM here by either the maximum or the minimum of its value reached in high density phases. And it's going to give a range of different observables, values of observables. Yeah.
Yep. Okay.
So yeah, then we move forward, and the main result, yeah, shown here in figure 3, when we first try to look again at extremes. If we assume the high density matter is causal, which is maximally stiff, the limit cannot be beaten by any realistic models. Yeah, this is a CS square equals 1. So remember, when I talk about the simple linear EOS for self-bound stars, by specifying M max, the x-axis, by specifying M max equals 2.0, which is conservative because we do observe heavy pulsars at these masses, then the black dot dashed line at the bottom provides actually the ultimate lower limit. Yeah, so if you change the speed of sound to be a small value, CS square equals 1/3, that lower bound also moves upwards, right?
Yes.
Yeah. So this is basically what the strange quark stars or self-bound stars would tell us about the minimum radius of a 2.0 solar mass star. And any other equational state with a nuclear matter input will lie above that bound, basically. And the
yes,
for colored bands, what I am going to describe now represent different combinations between the low density nuclear part and high density quark part. Right. Yeah, you may notice in the legend, I denote them by soft to stiff, stiff to stiff, soft to soft, and stiff to soft.
Mm-hmm.
So these are based on the two types of nuclear matter, EOS, we select at low densities, and also the two sound speed values we have chosen for quark matter. CS square equals 1 is for stiff quark matter.
Mm-hmm.
CS square equals 0.33 is for soft quark matter.
Okay. Mm-hmm.
So yeah, so these are broadly speaking, the very generic feature of all different combinations you can have big standard nuclear matter, and then transforming it through a phase transition into some high density quark matter.
Yes.
Yeah. So you may already realize for each color band, there is also a very interesting bond, lower bound. It increases from left to right because we have a different assumption of the Mmax, right?
Yep.
For example, this red band, the lower bound of the red band is not very far away from the strange quark star band, which is the lowest dot dash blacker.
Uh-huh. Yep.
Yeah.
Mm-hmm.
So, oh, you are looking at CS square equals 0.33. I'm looking at, yeah, right. So CS square equals 1.
Yeah. The cursor does not necessarily follow me. Okay.
Yeah, so what is the arrow mean? The arrow means we are moving from a very low critical phase transition density to a relatively high critical phase transition density.
Okay.
So the lowest point represents the lowest transition density for which we specify as the nuclear saturation density. So basically, we want to make sure at nuclear densities, we still have bulk nuclear matter, not bulk quark matter, because otherwise it's in contradiction with nuclear experiments, right? We do see normal nuclear matter at low densities, not quark matter. And that is a conservative bound again. And the vertical line, as it goes upwards, we have a slightly higher value of that critical transition density.
Okay. Mm-hmm.
Yeah.
Yes.
At some point, it stops. There are different reasons why it stops. One reason is following the direction of the arrow, as that critical density rises, the strength of a phase transition decreases. So that jump delta epsilon in the equational state, as long as it's finite, then we can say it is still a phase transition. But at some point, the width, or sorry, the height of that discontinuity drops to 0,
right,
which means there is no actually valid phase transition at all.
Mm-hmm.
So that's why the vertical line stops at some point.
Mm-hmm.
The other reason it might possibly stop is as we increase the critical onset density for phase transition, at some point, we are following the hadronic mass versus radius. At some point, we hit a value of, for example, 2.0 solar mass neutron star. There is one value of central density for 2.0 solar mass neutron star. If the critical density of phase transition is equal to that value, then we consider there is no interesting point to look at, because all neutron stars below 2 solar masses are actually purely hadronic ones.
Mm-hmm.
Yeah, that is another reason. Although this cutoff is kind of artificial, one can always choose a different value for that critical cutoff, simply because we do not believe high density transition density as high as a central density of a 2 solar mass neutron star.
Mm-hmm. Yes.
Yeah. Yeah. And also this general trend you can see as the assumed value of the maximum mass increases from left to right. So basically R 2.0 predicted from all different types of models tends to rise as well. Yeah, from 2 solar mass, for example, to 2.4 solar mass. Yeah.
Yep.
Right.
Yep. Wow.
And the differences between, for example, the red and the blue band is much wider in general for different values of maximum mass. The main reason is it starts with a relatively stiff nuclear matter, which means the hadronic branch is with some high value of radius for canonical mass neutron stars. And with phase transitions, by the way, for the hadronic matter only scenario, we also show them on the plot as the asterisks. So the two stars on this plot represent the value without a phase transition at all. Just use the hadronic baseline. We have these two, these two stars. And basically, one can start with a hadronic baseline, roughly the value shown by these two stars. With phase transition, it's possible to achieve much smaller values because of that discontinuity, which softens the equational state. And that's basically the reason why the blue band is wider, right? Because the hadronic equational state itself is stiff, which gives a slightly large radius. And then by including phase transition, one have multiple possibilities to decrease that value. Right. So this is saying the different ranges of radius are covered by different combinations, and the blue band is showing we can have many possibilities if there is a steep to steep phase transition. Yeah.
Nice.
Right. This is basically the main result of our paper, and all others are just, for example, varying parameters in the quark phase as changing its stiffness. Yeah.
Okay. So for example, let's take a look at B here.
Yeah, panel B is a permutation of panel A, but we want to show what future observation data can tell us. And again, the y-axis is still the radius of a 2.0 solar mass star, and x-axis is actually along the vertical line of the previous panel. So from left to right, we start with a very small transition density, saying at nuclear density, there is already a phase transition.
Okay.
So that corresponds to the smallest possible radius. Yeah, the title of our paper is the minimum radius of high mass neutron stars, right? So yeah, so the conclusion is this lower bound, this minimum value is always determined by phase transition at the lowest possible density, which we assume is nuclear density. Then transforming it to the maximally stiff matter, which is causality CR squared equals 1. And slightly, we can have a variance because of the different nuclear matter models we have chosen. That is, for example, between the red and the blue. The blue, again, is using a stiffer nuclear matter. Yeah, the red is about softer nuclear matter. And then you can see the minimum value for R 2.0 slightly different because of that nuclear physics input. Yeah.
Good.
Right. So the different contours about maximum mass are also shown here, which is important because we constrained Kershon state from different sources and different observations. Not only just one radius for typical mass, but we can do a joint constraint effort. For example, if we specify a lower bound on Mx equals 2.0, which is true, the case. And also, if we have an upper bound on the radius of a 2.0 solar mass star, indicated by the arrow here. Then you can see the green curves and the brown curve, very, very short segments. They are ruled out. Right? There is no way to explain both 2.0 solar mass pulsar and value of R 2.0 smaller than 11, I think it's 11.5 kilometers.
11.5, yeah.
Yeah. So this is showing how different constraints from different perspectives can help eliminate part of the parameter space.
Good.
Yeah.
Very nice.
Another way to look at this is if we have a upper bound on the maximum mass. For example, Mx smaller than 2.1 with a lower bound inferred from, for example, nicer data on R 2.0. And also we have shown this hypothetical measurement, the arrow going upwards. And this is saying, yeah, some parameter space can be ruled out. For example, the green dashed curve, yeah, the part of that green dash curve with the too high value of R 2.0 is ruled out. So what does that mean? So that part corresponds to a phase transition into maximally stiff matter, but at densities relevant for canonical mass neutron stars. So the x-axis is showing above a certain value of the mass. There is a Park core in the neutron star. The x-axis is called M trans. It's a proxy for this transition density, what we called N trans or P trans before.
Right.
Yeah. So the combination of these two constraints will be able to again rule out certain parameters in this framework.
Very cool. Very nice. Figure.
Yeah. So when we do a little bit discussion on what this really means, for example, if we can have a bolder estimate for the maximum mass, which we show in figure 4. Yeah, what if the maximum mass is actually 2.3 or 2.4 solar mass? Right, so that will further constrain the, for example, allowed region for the radius of 2.0. And now it's more likely that the radius of massive neutron stars tend to be also larger.
I see. Okay.
Because that band, you may notice the band itself goes thinner and thinner if you
Right.
increase the maximum mass.
Okay, that makes sense.
And a different region on the QCD phase diagram is going to be, for example, high temperature low density region. So there is this speculated first order phase transition line on the QCD phase diagram. And what we can actually probe is what is the maximum chemical potential being reached in massive neutron stars. Usually, for example, people who do heavy ion calculations, they tend to show QCD phase diagram as temperature versus chemical potential. And at the top left part, there is region probed by LHC, right, by RIG, by heavy ion calculations.
Yeah.
And the bottom right panel is where neutron stars are. And to connect the different regions, there is a hypothesis about whether there's a first order phase transition or not. And if we have an idea of the maximum chemical potential reached in neutron stars, then possibly we can try to connect to predictions about where that first order line might end if we, for example, further go out to finite temperature regions. Yeah, and yeah, that is basically why we decided to also show a plot for central densities and central chemical potentials. Yeah.
Okay.
Right, we follow the scheme of calculations, but again, extracted those two important properties in figure 5 and figure 6.
Yeah, number density transition, central, okay. Relative to,
So this is again, along axis is where we have increasing density of that critical onset of phase transition.
there's the chemical potential, okay.
Right.
Okay.
So the central density of the maximum mass star is quite sensitive to what you assume the maximum mass of a neutron star is. So comparing panel A and panel B, there is a decrease basically in n central of maximum. Right. So the extreme case is we can have central density as high as like 9 times nuclear matter density. So the panel A, the uppermost curve, the red uppermost curve is giving a very high value of that central density.
Wow. If
we have evidence for a 2.3 solar mass neutron star, that maximum value is now only 6 times saturation density.
Yep.
Yeah, and it will keep decreasing. For example, we did an estimate after the announcement of GW9814, a possible candidate for very heavy neutron stars. For example, if we do have a 2.6 solar mass neutron star, what does that mean? Yeah, even in this unrealistically, extreme case, the central density is going to be smaller again, right? By increasing the assumption on maximum mass. So in that case, yeah, we find it's closer to 5 times saturation density.
Yes.
Yeah. This is also interesting because there is evidence from people who do simulations, merger simulations. We know eventually we will detect post-merger gravitational wave signals and then compare them to simulation results. So there is a evidence that what is the highest central density reached in merger remnant possibly can be extracted from post-merger simulations. So that's why we're interested and we want to show this relation. Because in the future, we all have different probes on different aspects, and they will be collected and compared together.
Cool. Nice.
So the chemical potential is simpler in the sense that the variation of this maximum value does not look very, very drastic. Yeah, unless if we have very soft high density matter denoted by the green and brown curves. So basically they have shown that chemical potential cannot exceed, for example, 1600 MeV. But it's an interesting property to look at because at ultra high density, at asymptotically high density, we should have predictions from perturbed QCD, right? That's going to be ultra high densities, and the maximum chemical potential shown here is from neutron star observables, and they should be still far apart from what perturbed QCD tells us. Yeah, and we finally had some discussion about the sensitivity to what kind of nuclear matter you chose at low densities. The table 3 is a summary of differences between them. Yeah. So our main results were performed by different combinations between nuclear matter and quark matter, and there is differences, of course, between the two cases. We have two hadronic baselines we have selected, of course. Yeah.
Okay.
So in general, one stiffer US, the other one is softer, which means a smaller radius and a smaller maximum mass.
Yes, indeed.
So the first two columns, P saturation and this L parameter, they are important parameters for low density nuclear matter calculations and also constrained by laboratory experiments. So we have reliable constraints from both theory and experiments on these two parameters because they are only parameters near the saturation density. But still, these two models, right? You can see there is a difference in these two because this range is of both L and PSAT is allowed, still allowed by the current uncertainties in low density nuclear matter. But above that density, the two equation states have their own behavior at high densities, and that's why neutron star observables are important because they are going to be used to constrain high density behavior.
Yep. Yes. Okay.
So based on the two equation state of nuclear matter, what will neutron star observables constrain in different ways on this phase transition is shown by figure 7. Now we have a comparison between the two nuclear matter models when a maximum mass of neutron star is being imposed. So the curves are showing basically what part of the region is ruled out by a massive pulsar.
Let's see.
Yeah, you can see there's a big difference between the blue and red, right? Remember, blue is for a stiff hadronic baseline. Red is for a soft hadronic baseline. Right. By assuming maximum mass is higher than 2 solar mass, a big region is ruled out, is eliminated for the red contour. Basically, all parameter space above the red contour is eliminated for a soft, which is even worse if we have assumed max is 2.3. Yeah, you might observe that very short dot dashed corner, this red curve at the corner, which is also shown in the inside plot. Range of transition density from saturation to 1.5 saturation. Only this extremely small transition density is allowed for a soft nuclear matter.
Tight. Yeah. Very tight.
Very tight. Yeah. And this is something that low density nuclear matter and experiment is able to probe, basically.
Okay.
Yeah. If instead the nuclear matter at such low density is stiff, then we have more choices for the blue curves. Yeah. You can see there is a variance for quark core to appear at ultra low densities up until like very moderate value like 1.5 solar mass stars. So another thing worth mentioning is this plot itself also going to be sensitive to the stiffness in high density quark matter.
Mm-hmm.
What we show here is just one value. We assume the speed of sound squared is like 0.6. Yeah.
Right.
If we have only soft matter, then the excluded region will be growing again, which is worse. Which is worse.
It's even worse. Yes. If you go.
Yeah.
Purely hadronic. Yes.
Yeah.
Uh-huh.
Right. Exactly.
I'm with you.
Mm-hmm.
Good.
Yeah. So finally, we have some discussion about other constraints from different sources.
All right, because you got like various tidal parameters.
Yeah, exactly. So what we expect from different probes, from X-ray, from gravitational waves, from other sources.
Uh-huh.
Yeah. So of course, the standard constraint on the canonical mass neutron stars, like the radius or total deformabilities of a 1.4 solar mass star, is going to be further constrained after we detect more and more binary neutron star mergers. The total deformability is extremely sensitive to the radius, and more events will provide a much better estimate on that value, of course. As I mentioned, also the heavy pulsar lower limit on the maximum mass from, for example, Shapiro delay, right?
Okay.
Will be very powerful to eliminate parameter space for high density phase transitions. And there are additional sources of, for example, constraining the maximum radius from simulation of post-merger.
Right.
Assuming there's a prompt collapse or not, will give a different explanation. For example, it's generally accepted GW17 is a short-lived neutron star, and then after some time it collapses into a black hole. So that scenario, if we looked into detail by doing simulations, can provide a lower bound on the radius of that merger remnant, basically. Yeah, so this can be additional information if we observe more and more merger and then just perform more simulations to refine a little bit. Yeah.
Cool.
And lastly, we have also talked about other static properties which are important to constrain radius, for example, from moment of inertia observations. Yeah, and also we can constrain binding energy of neutron stars from supernovae, for example. These are all interesting and will be, I think, achieved in the foreseeable future.
Cool.
Yeah.
So, Sophia, thank you very much for walking us through this really lovely article.
Thank you.
And now that you touched upon the topic, you mentioned some of the future. So where do you think the community will head over the next, let's say, 5 years or so with regard to observations? Of course, cross fingers for more neutron star mergers. But what else can be done? Are there other observations that are in the pipeline over the next 5 years? Are there new calculations that should be done? Just sort of where do we go over the next 5 years?
Yeah, so in the next 5 years, in addition to more binary neutron mergers, we're going to observe. We already have updated data from NICER, right, on this pulsar JO740, first estimate of its radius. Now, since we have both information for both R1.4 and R2.0, then the different scenarios I talked about at the beginning, right? There are different equational states with very different features on the mass radius curve. Some of them might already be disfavored. For example, this third family neutron stars.
Yeah, okay.
The third family neutron star predict a drastic decrease in radius from 1.4 to 2.0 solar mass star.
Yes.
And now we have data from NICER, and this scenario is likely disfavored. Before the second NICER measurement, there was an alternative explanation for the small tile deformability inferred from GW17 over 17 and the slightly large neutron star radius inferred from the first NICER measurement. So that alternative scenario is exactly what the third family star scenario is talking about. But now we already see with new data from NICER, this scenario is likely disfavored. This is going to be the case in the future, in the next several years. NICER has a lot of targets with different information on their masses, which means we will be constraining different parts of the equational state better and better.
Okay.
Yeah. And also there is recent development from low density nuclear experiment, such as the exciting news early this year came from this Neutron skin measurement. Yeah, this is experiment of measuring Neutron skin thickness of lead 208 performed at JLab. So there we have shown this sensitivity to low density nuclear matter, 2 examples we have chosen in the paper. But basically, the PRX experiment is going to tell us what matter at subnuclear density look like.
Cool.
And yeah, which is interesting because the saturation properties correlated with neutron skin thickness tend to predict value of the stiffness in nuclear matter larger than what theory predict.
Oh, okay.
Yeah, so it might be a different scenario if we want to be compatible with both a low density nuclear experiment and also high density neutron star observables.
Right.
There's an interplay between different aspects. Yeah. So we are going to narrow down the single curve of pressure versus energy density from subsaturation to some intermediate density and then to ultra high density, realizing neutron star cores. So this is going to be the main task for different communities in the next 5 years, I would say. Yeah.
That's
Another
awesome.
example would be if we accidentally detect some low mass neutron stars, like 1.0 solar mass neutron stars.
Oh, okay.
That would be great news. Yeah, that would be exciting because we can directly compare low density nuclear cosmology to the properties of a light neutron star. Yeah.
Nice.
Yeah, but we haven't seen them yet.
Not yet. Not yet. But lots of exciting stuff.
Yeah, it's emerging field. Yes.
Yeah. Well, yeah, it's been completely revitalized, so it's very nice.
Yeah, I still remember when I just began grad school in 2010, the same year when the 2 solar mass pulsar was detected.
Yeah.
Now we have 3 or 2 more of them, and this is going to advance the field even quite a bit.
Hopefully we get another 5, 10, 15, 20, and then we'll maybe hone in on the answer. So very nice. Sophia, I want to thank you so much again for
Thank you, Frank, for having me. Yeah.
Thank you. All right, everyone, that will do. Thank you very much, and we'll see you on the next one. Bye-bye.
Bye.